Hello and welcome to this video on the Wheatstone Bridge circuit. In this video we're going to be looking at the Wheatstone Bridge and how it works, and more importantly how it can be used to measure resistances. In this particular example we're going to look at how we can balance the Wheatstone Bridge circuit in order to determine an unknown resistor, and you can see the unknown resistor here marked on our diagram as Rx. So the Wheatstone Bridge, to begin with, is characteristically drawn in this way as a sort of diamond arrangement of resistances. So I've got on my diagram R1, R2, R3, and then our unknown resistor Rx, which is the resistor we're trying to determine the value of. So the Wheatstone Bridge, first of all, is a circuit that's designed to determine unknown resistances, and it's a little bit antiquated now because we live in an age of digital multimeters and different devices which can easily measure resistance. This was a kind of an old-fashioned technique used to try and figure out the value of unknown resistances by taking advantage of something that we've mentioned in one of our previous videos, the potential divider rule. And we're going to use the potential divider rule in order to balance this circuit. And when I say that we're going to balance it, we want this voltage that we've got marked on here, I've called it V out, the output voltage. We want this voltage to be 0. And if it's 0, then the circuit is balanced. And so if our circuit is going to be balanced, it means that this voltage here should be equal to this voltage here. It doesn't matter what the voltage is as such, as long as those two voltages are equal, then the voltage across V out, or the potential difference, will be 0 and the circuit will be balanced. And we'll see how by balancing the circuit we can determine the value of our unknown resistor. So that's where we're going to begin, but to start with I think it's probably best if we redraw this circuit in a manner that resembles potential dividers a little bit more clearly along the lines of what we've looked at previously. So here I've redrawn the circuit in a manner that I hope is a little bit more approachable than the sort of strange diamond arrangement that we had on the previous slide there. First of all, you can see that our resistors form two potential dividers. We've got a potential divider formed from R1 and R3. And we've got a potential divider formed from R2 and Rx. And they're both supplied by our supply voltage here. So the supply voltage is going to be split into two voltages across R1 and R3, which will add up to the supply voltage. And that supply voltage will also be split into voltages across R2 and Rx, which will add up to our supply voltage as well. The one last thing to add in is to remember that we're measuring the potential difference between this point here and this point here, and we call that V out. And so our output voltage we're measuring across the gap between the two midpoints of those two potential dividers. One other thing worth mentioning is these resistors might not be notated in the same order as I've done here, but the principle is the same no matter which resistors are R1 or Rx, that kind of thing. So we're going to go ahead and we're going to try, first of all, and understand how we can balance this circuit, like we talked about before, and how balancing the circuit will help us find Rx. One thing that we haven't mentioned so far is that for the Wheatstone Bridge circuit to work, and for us to be able to use it to determine the value of our unknown resistor Rx, one of our other resistors needs to be a variable resistor. And it doesn't actually matter which one. It could be R1, R2 or R3, but one of them needs to be a variable resistor. And so for our example, we'll make R2 a variable resistor, which is denoted by that sort of diagonal arrow going through the resistor there. So R2 is a variable resistor, and we know the range of values that we can set R2 as. In real life, this is usually a long resistive wire, a sliding wire sort of scale that we can adjust the resistance from a very small to a large resistance by moving the slider across the resistive wire, and we'll know the range of possible resistances that we have available to us. Let's try to understand this circuit a little bit better with the aid of a practical example. So let's put some values in the circuit that we have here, and we'll say that our supply voltage is a voltage of 9 volts, and let's say that R1 has a value of 20 ohms and R3 has a value of 10 ohms. And for the time being, we'll just look at this left-hand side potential divider arrangement. We'll come to the right-hand side in just a minute. So first of all, the point of this circuit, or the aim of this exercise, is to balance the circuit so that V out is 0. Let's first of all find the voltage at this point here, the midpoint between R1 and R3. In a few minutes we'll do the same on the right hand side, but we'll look at the left hand side to begin with. This midpoint between R1 and R3 is the voltage at this point here, and let's refer back to our potential divider rule, because the voltage at this point here is the same thing as if we measured from that point with respect to 0. So we're measuring, if we imagine a voltmeter in the circuit, we're measuring the voltage there. And what we can see is we're actually measuring across R3 in a sense. And so referring back to our potential divider rule, we know that we can say that we'll call V3, the voltage across R3, we know that V3 is equal to the supply voltage, Vs, multiplied by a fraction, and we're measuring across R3. That's what our voltmeter that we've sort of put in our circuit here. We're measuring with this point, at this point here, with respect to the 0 line at the bottom of the circuit. We're measuring this voltage here, which is the same thing really as measuring across R3. And so R3 goes on the top of our circuit. And on the bottom of our circuit, both resistances in our potential divider added together. So that's R1 plus R3. Remember, we're just looking at the left-hand side potential divider, which works independently of the right-hand side. And so if we put some values in our circuit here, in our equation rather, we've got 9 volts as our power supply, multiplied by R3, which we know is 10, so 10 on the top there, over 20 plus 10 on the bottom. And so that comes out as 3 volts. And so what we find is we have a voltage of 3 volts at this point here. Remember, the aim is to balance this circuit for the difference in voltage between the left and the right hand side to be 0. And so if this side is 3 volts, we also want this side to be 3 volts as well. Remember, on the right hand side, however, one of our resistances is unknown. We don't know the value of this resistor Rx. We do have a variable resistor which works on a sliding scale. And so let's suppose, for the sake of example, that we've adjusted our variable resistor R2 until the voltage V out is 0. And we've done some back and forth with our variable resistor, and eventually we've got that V out to be 0, and that's happened at a resistance of, let's say, 33 ohms. And so the question is, what is Rx? Well, in order to determine Rx, we first need to do the right-hand side potential divider. Much like we did on the left-hand side, we want to find the voltage at this point here and we want to know that it's the same as the voltage on the right hand side. How would we express that as a formula? Just like the same as last time, we're measuring a voltage from the midpoint with respect to 0, and so we're essentially measuring across Rx in our potential divider. And so if we were to write that as an equation, much like we did on the left hand side, we'd have the voltage across Rx, which we'll call Vx. I'll write that here. Vx is equal to the supply voltage, Vs, multiplied by a fraction, and on the top of that fraction is Rx, because we're measuring across Rx. On the bottom of the fraction, both resistances added together, so that's R2 plus Rx. Now, we know that we've managed to balance our circuit. We've balanced our circuit by adjusting the variable resistor until it has a resistance of 33 ohms. And so now our circuit is balanced. We know that we must have 3 volts on this side because we calculated that, 3 volts. And now that it's balanced, this must also be 3 volts. So I know that Vx is 3. Once more, I know that V3 is equal to Vx. They're both 3 volts. So again, V3 is equal to Vx. It has to be for the circuit to be balanced. And so we're going to do a little bit of algebra here to come up with an equation to find Rx, the unknown resistance in our circuit. And we're going to do this by taking advantage of this equality here, V3 being equal to Vx, because we know the formula for V3. It's Vs multiplied by our fraction on the left hand side, R3 over R1 plus R3. And we know that that's equal to Vx, and we said that Vx was Vs multiplied by a fraction, Rx over R2 plus Rx. So again, we're saying the same thing really. 3 is equal to 3 on the left and the right hand side, or we can say that V3 is equal to Vx on the left and the right hand side, or we can say that Vs multiplied by a fraction on the left hand side is equal to Vs multiplied by this fraction on the right hand side. They're the same 3 equalities, really, just expressed in different ways. But expanding them in this way allows us to do a little bit of simplification, hopefully, and determine the value of Rx as a formula. So let's have a look at our equation that we've got so far. One of the things we can do straight away is cancel out the Vs's. They don't matter in this particular formulation, and they cancel out on each side. And so we're left with R3 over R1 plus R3 on the left hand side, and Rx over R2 plus Rx on the right hand side. We need to simplify our formula further though, and the best way to do that with a formula like this, which is made of 2 fractions on either side, is to multiply each side of the formula by the denominator of each side. So what do I mean by that? Well, we're going to take the denominator, the bottom of the fraction on the left hand side, R1 plus R3. We're going to multiply both sides of the formula by this denominator here. And then we're also going to do the same on this side. We're going to take the denominator of this side, R2 plus Rx. We're going to multiply both sides of the equation by the denominator here as well. Let's have a look at what happens. So first of all, when we multiply both sides by R1 plus R3, well, R1 plus R3 is going to cancel on this side. We're dividing by R1 plus R3 to begin with, so if we multiply by R1 plus R3, those are going to cancel out. But we have to do it to both sides, and it doesn't cancel out on the right hand side. We're multiplying by R1 plus R3. Likewise, we can do the same thing with the denominator on the right hand side. So we can say that by multiplying both sides by R2 plus Rx, R2 plus Rx is going to disappear on the right hand side, but we have to multiply on the left hand side as well. So we have R2 plus Rx. So we've made a mess of our formula here. Let's rewrite it a little bit more neatly, because on the left hand side we have R3, which is still there, now multiplied by R2 plus Rx. So we've got something that looks like this: R3 multiplied by, in brackets, R2 plus Rx, and that's equal to, on the right hand side, Rx multiplied by R1 plus R3. Okay, so we're getting somewhere, but we can do some more to simplify the equation that we've got here. Remember, the whole point of this exercise is to find Rx. And so what we can do is, to simplify this expression further, is expand these brackets and hope that some terms cancel down or cancel out. So to begin with, on the left hand side we've got R3 multiplied by R2 plus Rx. If we were to expand that, we'd end up with something like this. We'd have R3 multiplied by R2 plus R3 multiplied by Rx. So both of those terms in the bracket have been multiplied by R3. On the right hand side, same idea. We've got Rx multiplied by R1 plus Rx multiplied by R3. Okay, so by looking at what we have now in our expanded formula, can you spot anything that cancels out? Hopefully you can see that it's this term here, R3Rx. On the right hand side, Rx, R3, the same thing. Rx and R3 multiplied together. And so what we can do is subtract this term from both sides. And so this is gone and this is gone. And we're left with R3, R2, or R3 multiplied by R2, is equal to Rx multiplied by R1. And remember, we're looking for the formula for Rx. So a little arrangement dividing both sides by R1, we end up with Rx is equal to R3 multiplied by R2 divided by R1. Let's go back now to our example above, because we said that we'd balanced our circuit and we'd found that in order to balance it, this resistor here needed to be at 33 ohms. It was a variable resistor. We could have set a range of different values, but it so happened in our example, it so happened to balance at 33 ohms. The other two resistors are known resistors. And so finally, we can plug some of these values for R1, R2 and R3 into our formula, and we can determine the value of Rx. So let's do that to finish with. So, going back to our original formula here, we can now say that Rx is equal to R3, which we said, I'll double check, was 10 ohms. So that's 10 multiplied by R2, which was our variable resistor in this case, which we said was at 33 ohms, divided by R1, which we said was 20 ohms. And so we find that by deriving the Wheatstone Bridge formula and putting in our values, our unknown resistor Rx has a value of 16.5 ohms. One last point to make in this video is to say that we've obviously derived this formula for Rx by using the potential divider rule. But there's no need to do that anymore, providing that the resistors are termed R1, R2 and R3 and Rx as we've done in our example. You can simply place your values straight into the Wheatstone Bridge formula to determine the unknown resistance. One quick word of caution with doing that though, because the formula that we've used assumes that we have our resistors called R1, R2, R3 and Rx in our formula here, in our circuit diagram, sorry. And it assumes the position of these resistors. In my example here, R1, R2, R3 and Rx. Some textbooks and different examples you might see have R1, R2 here, R3 here and Rx here. Now, if that's the case, it doesn't actually affect our formula because, as you can see, R3 and R2 are multiplied together on the top of our fraction here, the numerator of our fraction. And if R2 and R3 are the other way around, we get the same result. We're multiplying them together anyway. But just watch out in case the position of the resistances has changed otherwise. If Rx, for instance, the unknown resistor might be on the top or it might be on the left hand side, and that might change the arrangement of this formula. But nevertheless, we can still use the potential divider rule to derive the equations for both sides, the voltages on each side of the bridge, and then by equating them we can derive a formula for the Wheatstone Bridge unknown resistance. So I hope you found this video useful. First of all, in understanding what the Wheatstone Bridge is and how it's used to determine unknown resistances, but also by applying some of the concepts that we've covered previously, such as the potential divider rule, in order to make that Wheatstone Bridge formulation work.